So thank you all for coming to class. Um, those of you in the South Bend area may have been panicking or rejoicing, I don't know, without internet for a little while. I know my wife was a little disappointed when it came back, but it's okay because it kept us from having to break out actual physical DVDs to watch with our kids. I don't know, it's a mixed bag. So here we are. So today is the second and final lecture about momentum. This is chapter 6. And before I launch into whatever it is I'm going to talk about, let me ask, what questions do you guys have? Okay, good. That's cool.
Hey, Professor.
Yes, please.
I have a question, but it's over the quiz 5. Should I just ask it next time? Or
Ask it now. That's fine.
okay, there is a problem on there here. Let me get to it. It was like most electrical appliances are rated in watts. Does this rating depend on how long the appliance is on? Could you explain that a little bit? Because
yes, I can. So this. So a watt, not yellow, come on. A watt is a unit of power, except sometimes we use W for work as well. So let me actually write watt out. A watt is a unit of power, which is a rate, right? Power is energy use per unit time. So the power usage of a device does not depend on how long it's plugged in. The total energy that it uses depends on how long it's plugged in. But the power consumption, it's kind of like asking for any other rate. Like, does let's say a car is driving 60 miles an hour. Does the speed of the car depend on how long it drives at 60 miles an hour? The answer is no. The distance it travels depends on how long it drives at 60 miles an hour. Right? So the crux of this question is basically that power is a rate, and so the rate doesn't depend on time, but the numerator of that rate does. Does that answer your question?
oh, yeah.
Okay.
Awesome. Thank you.
Of course. Other questions? Okay. So let's finish this up. And if we have some time, because I worked all of the last 3 lecture examples in the pre-lecture videos. So I don't have other examples. I might reference those. But if we have an extra 10 or 15 minutes, I might talk about the practice exam for the exam we have coming. We have an exam on Monday. Now, as I did before, you don't have to take the exam on Monday. I'm going to open it up, I think, Friday, if I can get it all entered into Canvas, and I'll leave it open till Wednesday. So that's a broad range. I want to give you flexibility so that you can catch up if you feel like you're behind. You can take it at a time that you feel comfortable. Yeah, so I do want to talk about that a little bit so that I can address things like, how do I know? Because it's 4 chapters. It's chapters 4, 5, and 6, which is, it's not 4. That's 3. It starts with 4. It's 3 chapters. I'm glad I'm not recording this to post on YouTube. Like, oh wait, crap, I am. Yeah, it's 3 chapters, 4, 5, and 6, and they're all kind of different, right? That's 4 is like dynamics problems, like F equals ma. 5 is work and energy, and 6 is momentum. And the approaches to the problems are kind of different, right? So how do I know which approach to use? I'm hoping to get to that by the end of today's lecture. The other thing I wanted to say, I have not finished grading exam 1 because I'm fitting it into the cracks of time and whatever, which is probably what you're doing with this course, and I understand that. But I've graded about half of them, and the average so far is 88%. So you guys are doing well. I'll hopefully have those finished. I'm going to try to do it tonight, unless I fall asleep in the chair, and that might happen. Sometimes that happens. Okay, so let me finish chapter 6. I don't think that's the screen I wanted to share. Can you guys see me scribbling on the screen?
Yes.
Yes.
Okay, good. For some reason, it's not highlighting that. Okay. So, again, we're talking about momentum. Momentum is the product of an object's mass and its velocity. And it's super useful in collisions. So when we use momentum, often we're talking about collisions, which I'm sure I didn't spell correctly. Oh, it's okay. So in a collision, right, we have an object. We could even have an object hitting a couple other objects, right? So here's my before. Let's move that so I can actually label it. And an after. So let's just choose an after. Let's say there's a V initial. Let's call them 1, 2, and 3. And afterward, maybe this guy's still going this way, and these two guys are going off that way. So this one, this guy will have slowed down a little bit probably. Okay. So if the only forces acting here are internal to the system, which means the system is just a collection of objects. So here it looks like I'm choosing objects 1, 2, and 3 to be the system, right? This could be like a cue ball hitting 2 other pool balls, right? In which case this wouldn't actually have a 1 on it, right? But the others could actually have a 2 and a 3. If the only forces acting here are forces between those objects, I expect momentum to be conserved, which means the initial momentum, right, P initial equals P final, right? And what I mean by capital P is the sum of all of the momenta. So like P1 initial plus P2 initial plus P3 initial, come back. Right. And so this is the law of conservation of momentum, just like we had conservation laws before, or a conservation law for energy, right? Just means it does not change in time. So there's that, and then I've got P1 final plus P2 final plus P3 final. And momentum is a vector, right? Because it's mass times velocity, and velocity is a vector. So that means it has components. So I should write vector signs over all of these. And that just means it's conserved in the x direction and conserved in the y direction, as long as there are no external forces in those directions. Might even be conserved in the z direction. If these are pool balls, the z direction would be like the direction of gravity, and x and y would be the plane of the table. That's true unless there's an appreciable friction force between the pool ball and the table, and then it might slow down. You might actually lose momentum. Okay. So I did a 2D example of this But because I'm not sharing the, oh, you may actually be able to see this. No, there I go. If I minimize, I see why. If I minimize this, now you can see my folder, right? I'll take that as a yes. Okay. Here, so here's an example of a 2D momentum conservation problem, and again, I worked this one on the videos, right? And I don't expect momentum to be conserved in this problem. This is a firework being fired, right? So it's in midair. Just before what I've labeled before, it would be going just a little faster. And if it hadn't exploded, just after what I've labeled before, it would be going a little slower because it's just in projectile motion. But for a brief moment, right, during this explosion, we're ignoring gravity, and that's because the explosion force is so much bigger that momentum is conserved mostly, right? The momentum change due to gravity is so small that we can ignore it for a brief second. And that's enough to figure out the trajectory of these three particles, or the three like bits of the firework. All right, so again, and we're just bringing it into X and Y components. And I wanted to mention something that I haven't mentioned before, because if I mentioned it before, I'd be repeating myself. I do that too, it's fine. We didn't break energy into components. When we said E initial equals E final, we didn't say E initial X equals E final X. That's because energy is not a vector. Energy is a scalar, right? Energy is just a number. It doesn't have direction. Even kinetic energy, it feels like you could say, oh, an object has kinetic energy in the same direction as its velocity. But again, energy does not have direction. So we didn't have X and Y equations for it. But momentum is a vector, so it does have direction. And so we can break it into components. All right. Other questions? So let me reference, you know what, let me talk about this. So we've got this before and this after, and you can't see it because I minimized it, so let me bring it back. There. So we got this before and this after for this problem I kind of sketched, like I just made up. And there are actually lots of ways for momentum to be conserved here, right? Depending on how you hit these balls, right? Kind of where the where V initial lies relative to 2 and 3, you could have these two, the two balls that it hit go in the directions that I've shown, or they could go off like more straight. And if they did that, then V final for the bigger object here would have to be smaller, or they could go off like straight up and straight down, or more straight up and straight down, right? So what I'm saying is there are lots of ways for this collision to happen, and momentum could be conserved in all of them. You can actually show this mathematically, but that's pretty dry. And I was going to say, I try to avoid dry things. That's not true at all. I teach physics. I do lots of dry things. But that's dry even for my taste. And I want you to stay logged on. So there are lots of ways for momentum to be conserved here, but there's only one way for momentum and energy to be conserved. So sometimes we'll put an extra constraint on a problem and say, I also want mechanical energy, like the kinetic energy, sometimes potential energy, to be conserved in this system. And that, again, only has one kind of answer, and that is a special kind of collision. So a collision, yes, collision in which both momentum and energy are conserved momentum and energy. Is called elastic, or more correctly, perfectly elastic. So energy is also elastic, I swear. Energy is also conserved in a perfectly elastic collision. The kind of the opposite of that is well, let me say this. I think I described this in one of the videos, so this is a little bit of review, but I think that's not always a bad thing. So if energy is not conserved, we call that inelastic. And let me say, the law of conservation of energy is a law. So energy is always conserved. But what I mean here is mechanical energy, meaning kinetic and potential. So and in an inelastic collision, we've lost some energy to something else, like friction. Maybe it left as heat. If you have two objects hit each other and one of them gets dented, or both of them gets dented, that takes some energy, right? The force deforms the object and does some work. You lost some energy there, right? The difference between that and like a rubber ball is a rubber ball will deform, but it springs back and you get that energy back, kind of like, I mean, literally like a spring, right? So you deform a spring, you store some energy and you get that energy back. Again, as opposed to if you deform the spring and it just stays stuck, you lost that energy. There's a special case called perfectly inelastic. Inelastic. And in that case, the objects stick together. All right. And two of the examples that I worked in the videos for today were an example of that. One of them was this one, where a skateboarder and a student walk, or they're coming toward each other, right? The walker jumps into the skateboarder's arms and they leave the collision together. That's a perfectly inelastic collision. So what does that mean? I don't think that it means anything more special than they stuck together. The nice thing about that is often we can treat the final object like it's one thing because they leave with the same speed. So you can do this. You can add the masses here. Instead of having mass 1 v final plus mass 2 v final. If the v final is the same, you can just factor it out. The other problem I worked in the pre-lecture videos was this one, where you have a conservation of energy problem and a conservation of momentum problem stuck together. This is a fun class of problems. I have another example of this. I can't remember if it's on the, I think it might be on the practice exam. I'll have to think about it. But you can break this into these two steps, right? So again, what happens here is object 1 comes in, hits object 2, and they stick together and compress the spring. So there's a collision, right? And immediately after the collision, there's a spring compression, right? So I do not expect energy to be conserved in that collision because they stick together. Imagine it this way. How would you get them to stick? How would you make sure that they stick? We could do something like put Velcro on them, right? But what is the Velcro doing? It's supplying like this other force that that absorbs some of the energy, right? Or you could use like double stick tape or something, but it's the same story. You have to do something to the system to make it happen. And so you're losing energy in whatever that force is that's making that stick together. So I'm not going to go through this because I already did it in the pre-lecture video. Let me ask, what questions do you have about this? That's fine if you don't have any. I'm going to bring up the practice exam and maybe we'll talk about that for a minute.
Hey, Professor, on the exam, will you let us know if it's or like perfectly elastic or inelastic, or will that just be like kind of figure out on your own?
That's a good question. Kind of depends on the problem.
Okay.
I might say in a problem, I might say they hit each other and they stick together. I'm not going to ask you to label it as perfectly inelastic. I may not use those words, but frankly, you can do the problem without knowing that it has that label.
Okay.
Yeah, I guess I could do something tricky like I could say this collision is perfectly elastic, and that would be a cue that you could also use energy conservation, but I'm not going to do that.
Okay. Thank you.
You bet. So here's what I'm thinking to do. I'm going to bring up the practice exam. I'm going to scroll down to the long problems, and I'm going to have you tell me which approach you think we should use. Because again, we've got 3 chapters here. We've got dynamics, we've got energy, and we've got momentum. The dynamics, what I mean by that is Newton's laws, like F equals ma. So let me bring that up. Okay, we're almost there. Of course. There. Okay. So, oh, also, right, there's no lecture on this coming Monday. If we had to cancel lecture today, I was going to actually have us have lecture then. So, kind of glad we're having it now. I was ready to do this, so. All right, yeah, let's talk about this problem. When I wrote this problem, this was a few years ago. I had been watching through the MacGyver DVDs. There are a surprising number of celebrities in that are in it before they were famous, like Cuba Gooding Jr. and Terry Hatcher, and who else is in it? I don't know. It's worth a watch. Okay, so the question I have for you guys is not what's the answer, but it's are we using Newton's laws for this? Are we using energy conservation for this? Or are we using momentum for this?
Newton's laws?
Newton's laws is how I would approach this. Your first cue or clue here is that I ask you to draw a free body diagram. I ask you to draw that here so I can give partial credit for the free body diagram. Yeah, and then ask for a maximum rate at which you can accelerate up the rope. So we need to calculate an acceleration somehow, right? Acceleration does not show up in momentum. Acceleration doesn't show up in energy. So it's going to have to be F equals ma, right? Does that make sense, you guys?
Yeah.
Cool. All right. So here's another question. Rope is used to pull crates. You've got coefficients of static and kinetic friction. And blah, 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 blah. So we could draw a picture. And I'm not going to go through the whole thing. I just want to draw the picture so that you can see what's going down. All right, so we're going to pull this guy with some rope. I think we know the force exerted by this rope is 500 newtons. And there are a couple questions. Calculate a normal force, and calculate an acceleration. So what type of problem is this?
Still Newton, isn't it?
It's still Newton. Yep. Yep. So we would draw a free body diagram. That's again a clue. Also helps me give you partial credit for this. Draw a free body diagram, and almost always the next step after drawing a free body diagram is to fill out Newton's second law in the x and y directions, right? So once I draw this free body diagram, I'm going to do the sum of the forces in the y direction equals m times ay, and the sum of the forces in the x direction equals m times a sub x. And in fact, that's what I'm hoping you will do with this problem. My apologies if you were hoping to use this for like blind practice, but here we are. This is what's going down. Okay. Problem number 24. Got a nice picture here. Block sits on top of a hill, slides down the hill, and I want to know how fast is it going at the bottom of the hill, and if it travels 25 meters, what is the coefficient of kinetic friction between the box and the ground? So let's look at letter A. What idea are you going to use for A?
Are you asking for formulas?
You could give me a formula. Really, I want to know, is this Newton's laws, is this energy, or is this momentum?
Is it momentum?
Go ahead, either of you.
Momentum?
So
I don't know which thing it is, but I would use potential energy and kinetic energy.
I would use energy.
So does that make it chapter 6?
Makes it chapter 5.
Okay.
Chapter 6 is momentum. And I don't know how I would use momentum to solve this problem. Often we can shoehorn an approach into any problem, but I can't think of that here. So what we want to use is conservation of energy, bottom line. So we're releasing this box from here. So this is initial. And then it's going to come down here and turn into a triangle, I guess. I don't know what's going on. This would be final. And at the bottom of the hill, it's got some speed, right? It'd be final. And all we've done is we've changed gravitational potential into kinetic energy, right? So we could say K initial plus UG initial equals K final plus UG final. And in fact, that should be on the equation sheet. Let's find the equation sheet. I have that here somewhere, right? Ha. Here. Yeah, more or less. You have to put some of them together. If you look at this one, right? Mechanical energy initial equals mechanical energy final. Mechanical energy is K plus U. And we don't have any springs, so I don't need to include spring potential. Here's my gravitational potential, and kinetic energy is up here. Okay, you guys buy that? Okay, so we could ask for this. Hey, Noah. We could ask for this. Could we have used kinematics, right? And the answer is yeah, but we don't know like the angle of the hill. Hi, buddy. Although, frankly, if there's no friction, all we really need to know is it's falling. It's kind of like free fall. It should have the same velocity as in free fall, but it would be a different direction. But energy is so much easier for this. Do you guys buy that? It's fine. It's fine. We're having fun. Okay, so let's look at part B of this. We have 10 minutes. Yeah, we're good. I've got another thing I want to talk about, but I think we'll get through this. So the ground at the bottom is level but rough, and it slides 25 meters and then stops. Right, so I know this distance to use a color. Boy. That's like a delta x here. And then it comes to rest. And the question is, what is the coefficient of kinetic friction between the box and the ground? Okay. So what are your thoughts on this? What kind of approach would you use? And you don't have to say necessarily just an idea. You could give me, like, sketch out what you would do.
I'll take a stab at it. To get the coefficient of friction, don't you need the horizontal forces over the vertical forces?
Yeah, so we're going to need the definition of friction, right? So we could say this kinetic friction times mu sub k times a normal force. That's definitely a chapter 4 idea.
Is that the right direction?
Yeah, so we absolutely need this equation.
Okay.
So then how do we use that? So we need to figure out, you're absolutely right. We need the normal force and the kinetic frictional force. So it might be useful to have a free body diagram, which we could draw directly on the object here. Right, so there's weight, and there's normal, and then there's friction. Right, and the friction's what's slowing this down. So that's useful. Looks like the normal force is going to be exactly equal to weight in this case, which is, again, a chapter 4 idea. So that gets me the normal force. So then I need to figure out what the frictional force is, right? I need a number. Oh, why did that not work? I need a number for friction.
You have to calculate it out, knowing the distance.
Yeah. So that for that you could use kinematics, right? And let me say, I know all of our ideas build on each other, but I will not require a kinematic equation on this exam, right? I tested that on exam 1. I try not to do things like that. You might have to convert centimeters to meters or something, because that's pretty ubiquitous. But even though it's a topic that you've taken an exam on and mastered, right? I'm not going to explicitly test kinematics on exam 2. And there is a way to figure, so kinematics is one way to figure out the acceleration, and then you can use F equals ma to figure out the frictional force. Or you can use the work energy theorem. You can say the work done by friction is equal to the change in the kinetic energy of this object, right? Because it starts with some kinetic energy here, right? There's some K initial, if I'm now calling this initial, and it's going down here to K equals 0. So we're losing all of that kinetic energy. So there should be some like negative number here. And that should equal the work done by friction. And work done by some force is that force times a displacement, times a cosine. So I could do that. Force times delta x times cosine theta. But this term is just giving me a -1 because the delta x is to the right and friction is to the left. So what I should have here is kinetic friction times that distance times a -1 equals whatever my delta k is. Again, it should be some negative number. And that would let you solve for the kinetic frictional force, which you can then plug back up into here with the normal force to figure out this number. And if you're freaking out because you feel like you would never figure out how to work this problem on a 2-hour test, this part of this problem is harder than I would ask on the test. That's why it's on the practice test and not the actual test. Okay, let me pause. What questions do you have? Does this make sense, you guys? Okay. So there are 4 long problems on the practice test. There are only 3 on the actual test. So it kind of makes sense, and I don't always do this, but it would kind of make sense. One of them's from one chapter, one of them's from another chapter. So this one must be a momentum question, right? So how would I know to use momentum conservation for this? And the answer is, I've got 2 objects and they collide, right? Momentum is useful for collisions. So if you have 2 objects hitting each other, it's pretty likely you're going to use conservation momentum at some point, right? And again, I might ask something like, I didn't here. I could ask something like, how much energy is lost in this collision, right? And that would just be looking for delta E. So you just take all the kinetic energies afterward and subtract the kinetic energies before, and you'd get however much energy lost. So let me bottom line this. Do I have enough space to bottom line? No, let me go back to the scratch page. Sure, that's great. Okay, so let me bottom line. How do I know? Nope. What approach to use? How do I know what approach to use? So I'm just kind of thinking like keywords. So Newton's laws. And really I'm thinking F equals ma here. If you're looking for acceleration, so if acceleration is involved, that's a pretty good indicator that that you're going to need to use F equals ma at some point. For momentum, if there is a collision, that's a pretty good indicator that that momentum is going to be your go-to, right? If you have 2 objects hitting each other and you can draw a before and an after, that makes sense. What else? For momentum, we also have like impulse. We talked about impulse. Yeah, I think another indicator here, if there's a collision, and if we can think about the problem in terms of before and after, momentum is probably a good direction to go. And then there's energy. And lots of times we can solve Newton's laws problems with energy, and it really doesn't matter. It doesn't matter which approach we use. Energy doesn't readily give us an acceleration because we're not talking about acceleration when we do energy, but energy does readily give us speeds. So if I could think of a problem in terms of before and after, and I'm looking for a speed or a height, let's just do speed. I have to write it to see if is it IE or EI? It's IE. I don't even know if that looks right. I don't care. Let's just say H.
It's EI.
Yeah, now you know my secret, Shane. I'm spell check dependent. Okay. Past this, guys, practice. Practice is the best thing you can do. So let me pause one last time and ask, what questions do you have? So again, you've got some time before you have to take this exam, so there's lots of time to prepare. I would suggest working through the momentum homework. Take a look at this practice exam. Work all of the quizzes, because there are lots of conceptual problems there, and I don't do lots of conceptual problems in lecture. I do it here and there, and I talk about like the theory of things, but getting a handle on the concepts really is the quizzes are a good test for that. So I think we're good. Thanks for your attention, and I'll see you guys next time.
I have one question.
Oh yeah, please.
If we end up like working through like catching up on like through the 3 chapters for the test, and we have questions like after lecture Thursday, like on Friday, or do you like are you willing to do a Zoom or like email?
Email for sure. A Zoom would be harder because you saw 1/4 of my children.
Right. Okay.
But yeah, you could email, and I will definitely have office hours tomorrow. I have office hours on Monday, and in fact, I'll be around during lecture time on Monday as well. So I've got an hour and 40 minutes of Zoom that I'll just talk to anybody who comes by.
Okay.
Cool. Other questions? Okay. All right. So have a great evening, guys.
Thanks, Professor.
You bet.